All right, in this video, we're going to collect a couple more examples. So our first example, we're going to consider the polynomial t to the fifth minus 3t cubed plus t squared minus 3. And if we sit here and we factor it, we get something like t squared minus 3 t cubed plus 1. Okay, so that's not, that polynomial is not irreducible. In fact, the t cubed plus 1, we can even factor further. We can factor that as, I think, minus 1 is the root. And we'll get something like t squared plus t plus 1 when we do minus 1. T squared plus t minus 1 when we factor that. Is it plus 1 or minus 1? Hang on. T cubed, okay, good. T squared negative, it's minus 1. Great. And so let's see, what should a splitting field be? Well, sigma should be q. We got to have the roots of t squared minus 3. Okay, so we need to add in plus or minus 3. But if we add in root 3, we also get negative root 3. So we only have to add in the positive one. We need to have the 0 of t minus 1. The 0 is 1. That's already in Q, so we're good there. And then the zeros of t squared plus t minus 1 are 1 plus or minus I root 3 over 2. But sometimes it's helpful to have a simpler description of these guys. And in this case, sigma is just q adjoin root 3 and then I. Because if we have access to root 3, which we do, we have access to fractions, so we can kind of cancel these. And then we could divide by the root 3 to isolate an I. And then similarly, if we have root 3 and I, we can build these other roots. So it's just that guy there. And so that's one example of a splitting field. And notice our polynomial wasn't irreducible, the one that we started with. It was actually a product of 3 irreducible factors. As a next example, we're going to look at t to the fourth minus 2t cubed minus t squared minus 2t minus 2 over q, which factors, again, as t squared minus 2t minus 2 and t squared plus 1. Okay. And the zeros are, if you apply the quadratic formula, you get 1 plus or minus root 3 and I, and plus or minus I. And so splitting field for f, let me actually subscript this with an f just to indicate it depends on the f, is q adjoin 1 plus or minus root 3 and then I. But we have 1, right? We already have the rationals, so this is really just the same as q adjoin root 3 and I. Okay, so that would be the splitting field here. And notice something. These guys are actually, I don't know what I was doing with these bars on the side here. Hang on. These guys are just equal. The polynomials that they came from are different. These polynomials are clearly different. They even have different degrees. And yet the splitting fields that we got are equal. Okay? So it's not necessarily the case that the association polynomial to splitting field is a one-to-one correspondence. Many polynomials will have the same splitting field in general. And then as a last example, both t squared minus 3 and t squared minus 2t minus 2 have q adjoin root 3 as their splitting field over q. Let me just be clear here. Over q, have q adjoin root 3 as the splitting field. Because the discriminant of the second guy is it's going to involve a root 3, okay? Or it's going to have 9 as a factor. Do I believe what I just said? Let's see, b squared minus 4ac is, sorry, not 9 as a factor, 3 as a factor. 4 plus 8 is 12. Yeah, so it has 3 as a factor. So you get your q adjoin root 3. So anyways, Both of these polynomials are irreducible by, say, Eisenstein's criterion, and yet they're not equal, and yet they have the same splitting field. Okay, so the association polynomial to splitting field is not one-to-one. In general, many polynomials will have the same splitting field.